I'm really honored to be speaking here today at Bronx Science, and today I want to explain a little bit about black holes. Now, the thing is, most explanations of black holes you see are either too pop science, they don't really delve into the depth of the actual math and physics, or they're too complicated and they use mathematical techniques that aren't really accessible to the average person. So what I'm trying to do here is to hit that sweet spot where it's accurate enough to not misinform you, but also it leaves out too much of the nitty-gritty math. Because as it turns out, special and general relativity is actually very tedious when it comes to solving the physical equations. First thing that you always hear when you look up what is a black hole is that a black hole is a region of space-time so heavy that even light cannot escape. So what does that mean in essence? Well, why can't light escape, first of all? That's the first question that you have to ask when you're looking at this definition, because no definition in physics should be taken at face value. So why can't light escape? What is light trying to escape from? Now the answer to that is, can you see this if I write over the text?
Yeah.
Okay. Yeah, okay. So, gravity is the exact force that light is attempting to escape from. Now, a black hole is very special for this reason, and a black hole is also for a reason. When you try to see most objects, a photon hits this object, bounces off, and reaches your eye. But the problem with a black hole is that instead of reaching your eye, it gets sucked in and never comes out. It provides the appearance that this area of space-time is completely void of light, making it, well, black. So, what is gravity? Well, I'm sure you all probably have heard of gravity and know the basics of how gravity operates, but the specifics, at least for Newtonian mechanics, is that it operates through this system. Now, what does that mean in essence? It means that if we have over here and an object that is very close to it, this radius, the closer you get, the radius is a much okay. The closer you get to the black hole, the larger increases. Now, if you have the distance between yourself and the black hole, that means that the force will actually go up by 4 times. If you cut it in a third, the force will actually go up by 9 times, which means that the force's increase gets faster and faster as you slowly approach the black hole, which means that objects will actually accelerate towards this black hole due to the force. So now, that's just a Newtonian view of it. And that doesn't actually explain why gravity occurs. But that's the best that you can do using elementary algebra. So what is light trying to escape, in essence? It's trying to escape this force of gravity. But why can't light escape? If you just try hard and hard enough, can't you eventually escape this force of gravity pushing you down? Well, no. Every single object has an escape velocity for its gravitational field. Now, for something like a rock, its escape velocity is practically 0 because its mass is really small and the distance away from it is usually pretty large, and of course the gravitational constant that dictates the force it exerts on you is also pretty small, and your mass is pretty small as well, which means basically everything contributes to make the force 0 in essence. Which means that if this rock is exerting practically 0 force on you, you don't need really any velocity to escape its gravitational field because it doesn't exert any force on you to begin with. But then you come to something like the Earth. Now the Earth has a moderate amount of mass, excuse my drawing, but the Earth has a moderate amount of mass, and and you're pretty far away from its center, and another. Okay, so the radius is pretty big, which does contribute to make the force smaller, but the mass of the Earth is even bigger. The mass of the Earth is huge, and your mass is decently big too in comparison to the Earth, and the gravitational. What the? Okay. Are you gonna close the door? Don't need Squidward singing "All I Want for Christmas Is You." Okay, great. What? Yeah, you're right. I mean, I haven't drawn on the black part yet, but okay. So now this has a decent amount of escape velocity, but its escape velocity isn't infinite. That's why we're able to send satellites and other things outside of the gravitational influence of Earth. But how do we precisely calculate this escape velocity? Okay, so how do we precisely calculate this escape velocity? Well, it all comes down to this equation. I'll just use the regular annotations for it. This equation, or you might be more familiar with seeing it as this. So the kinetic energy that you want to have at the beginning of your flight should be approximately equal to the potential energy that you have at the end. So what does that mean exactly? Well, it just means that you want enough velocity to keep being able to go away and away and away from it, even when you reach an infinite amount of distance. So if you're at 2,000 meters, you should still be able to go farther with your velocity. 20,000 meters still should be able to go farther. 200,000 still should be able to go farther, and so on and so forth. So this is where we derive the escape velocity, and we get that the potential energy that we use out there, while normally on Earth we use this equation, the thing is, well, when we're talking about rockets and the like, we're getting far enough away from Earth that its gravitational influence on us starts to deplete. Well, that's the whole point of escape velocity, which means that we can't set g to a constant like that. We have to use a more precise equation. And in fact, that equation is sort of analogous to this one. If you know the origins via calculus of how potential energy comes about, this equation right over here is going to make more sense to you. And of course, that's equal to the kinetic energy of our small little object right over here. Okay, then I guess I'll write it a bit bigger. Sorry. Have you checked your glasses? Oh, there's some empty space over here. All right. So, this gives us everything that we need to find the escape velocity of, for example, Earth. But a black hole is special in that it sucks in everything. Nothing can exceed its escape velocity. And of course, that means that its escape velocity, this is the escape velocity that we're solving for right here, has to exceed the speed of light. So, the first thing that we do is we see this common factor of m on both sides, m being the mass of the object that's being sucked in, and we can just cancel it out. We can divide it out, leaving it with this right over here. So we go on to write negative 2gm over r is equal to the escape velocity squared, and after that, v escape is equal to 2gm over r. But the black hole is special in that light can't escape. As I said before, that's why it's black, which means that we have to set this escape velocity right over here to the speed of light. So this will give us the radius that you need to compress something to for a given mass in order to make it into a black hole. Or in other words, the radius that you need to compress something into in order to increase its escape velocity to something greater than the speed of light, and thus make it impossible for anything to escape its pull at the end of the day. So that means that you can call this the Schwarzschild radius, as Karl Schwarzschild is actually the name of the person who first solved the Einstein field equations of relativity in order to produce the hypothetical black hole. And we get this equation after squaring both sides, this equation after taking the reciprocal, and this equation after multiplying both sides by 2gm. So this is the essential part of the black hole. This is the radius beyond which nothing can escape a black hole's pull, also known as the event horizon. So that's a very simple overview of a black hole, but can we go a little bit deeper? So first of all, a black hole is a region of space-time. But what is space-time? So when we describe the universe, we usually use 3 dimensions: the z, the y, and the x. I said those in backwards order. So these 3 dimensions describe the entirety of our universe normally. So, this is the Galilean framework of how things work. As long as you have this, and you know what your velocity is, and you know what your acceleration is, then you completely know everything that you need to know about this object. Nothing needs to be known about the time, for example. You can't really change the time. The entire universe is operating on one single clock. The entire universe will say that it's been 13.7 billion years since the birth of the universe. But that's actually not the case. Now, this form of mechanics is very widely studied, and also probably the version that you'll come to learn when you take Physics 1 and Physics 2, but this is not actually the true version of physics. Relativity changes this whole thing based on one, well, technically 2, but one very important postulate. And a postulate just means something that we can't really physically confirm, but we can experimentally test, and it's shown to be true. So the speed of light, which is denoted as c, is the same in all reference frames. Now, that should naturally not let you take this at face value either. To keep progressing, you have to ask, what is a reference frame? And to explain a reference frame, let's say you're in a car moving on the highway. Now, you probably know from the speedometer and also from the occasional jostles of the road that in this car you're moving at, who knows, maybe 60 miles per hour. But it's not like you actually feel the wind blowing against you at 60 miles per hour. It's not like you can feel yourself moving at 60 miles per hour, like you have that jolt against you. Instead, you're moving with the car. Does the car's position seem to be changing with respect to you? No. If you look down, you're still going to see the cup holder, no matter where you are. If you look up, you're still going to see the lights on the top. I forgot what they're called. That's not going to change. If you look right in front of you, you're still going to see the dashboard and the windshield. That's not going to change. no matter how fast you're traveling, because the car happens to be traveling with you inside it, meaning you and the car are going at the same rate with respect to the road, and thus you and the car you see the car as being at rest in your own reference frame, even though they're moving with, say, 60 miles per hour with respect to the road. But then the problem is, of course, when you are moving at 60 miles per hour and the car is moving at 60 miles per hour, and suddenly, I don't know, you made a really bad decision, and the car suddenly stops moving with 60 miles per hour with respect to the road. But you can't forget that you're still moving with 60 miles per hour with respect to the road, and the tree that you're about to crash into is at rest with respect to the road, which means that you're probably not going to survive this incident. So this is what a reference frame means in essence. But if you were riding an imaginary beam of light, I mean, you can't physically ride light, don't try it. But if you were somehow riding a beam of light, it's not like as the same thing as you would see if you were in the car. If you were to somehow ride a beam of light, then you would still see the light as moving at that rate of 3 times 10 to the 8 meters per second. And that right over there is what causes relativity to have such weird properties. You probably already know that the velocity of something is the change in distance that it makes over time, which means that if the velocity of something is forced to stay constant by the universe, then the concepts of distance and time that we have can't just stay constant too. They have to change and warp around depending on how fast you go. And that's expressed by what we call the gamma factor. So this postulate of general relativity, along with the other one about reference frames, allows us to derive a very nice theory for macroscopic particles. And that all starts with the Lorentz equations right here. Now, this right here is called the gamma factor, and it's a factor to essentially show how messed up you're making the world. So what this means right over here is if your velocity is way less than c, like for example 60 miles per hour, then your velocity divided by c all squared is going to be basically 0. And what does that mean? The gamma factor is going to be equal to 1 divided by basically the square root of 1, which is just equal to 1. But if you're moving at, say, I don't know, what's a nice number? I guess, oh, okay, that works, I guess. If you're moving at, say, 0.71 c, or the square root of 2 over 2c, if you're moving at 0.71 times the speed of light, what's this going to look like? Well, v over c squared is going to be approximately 1/2. Okay, that actually doesn't look as good as I thought it would. I'll just use a simpler number, like if you're traveling at half the speed of light, for example, what will this look like? You'll get 1 divided by the square root of 1 minus 1/2 c over c squared, which you can figure out is 1 minus 1/4, which is, of course, equal to 2 over the square root of 3, which is actually equal to, just off the top of my head, I'd say about 1.7 is what I'll say off the top of my head. So if you're traveling at half the speed of light, this is 1.7. If you're traveling really slow compared to the speed of light, this is 1. But you'll figure out that as your velocity approaches c, this is going to reach an asymptote. I mean, if you plug in 0.999c, you get this right over here. 1 divided by 1, the square root of 1 minus 0.999 squared. And of course, I'm not going to say that off the top of my head, but that's very, very close to 1,000. And you can see that if you just straight up plug in c, you just get 1 over the square root of 1 minus 1, which gives us an indeterminate value. So that means that as you get closer and closer to the speed of light, you gradually mess up the world more and more from your own perspective, especially your perceptions of space and time. Now, if you would remove this, so if you were to remove this and this and this, then this looks like a completely normal reference frame and one that you would probably study in Physics 1. But suddenly, with the inclusion of these, now your perception of the world is completely warped. And these are the contributing factor to that. So this is what we call the Lorentz transform. So this is just another slide that I thought would be good to explain how reference frames work, but I think I've explained them adequately enough. So let's move on to the second question. Originally, we said, it's a region of space-time that's so heavy, not even light can't escape. Not even light can escape. But what is light trying to escape? Gravity. Now, the thing is, you will probably recall that I said that the force of gravity is equal to gmm over r squared, which means that it's proportional to the mass of the object being sucked in. But wait, light has 0 mass. Photons have no mass. So if I plug in 0 right over here, no matter what m and r are, won't I just get 0? How is light physically influenced by gravity? So first of all, this is a small slide explaining how exactly we measured the speed of light, and it's actually a very interesting setup by Leon Foucault. But to keep it short, a bit of light entered a slit, after which it would hit a very rapidly rotating mirror, be focused into a lens, be focused onto a specific spot on a mirror, reflect back into the lens, be focused onto this rapidly rotating mirror, which is now in a different position, and go all the way back into the slit. And the difference between the hole where the light originally came through and the reflection of the light allowed Foucault to measure the speed of the light, given the speed of this rotating mirror. But what's more interesting than this setup, which was invented in 1862, is, of course, what I just mentioned. Photons have no mass. So how can they be affected by gravity at all? So here's the thing. This is where we get into how space-time actually works. Now, space-time, if there's no mass in it at all, if space-time is a complete vacuum, there's nothing in it at all, then this matter-energy distribution is equal to 0. It's not warped at all, it's just normal Euclidean space. It's completely flat. But if I provide a gravitational influence, if I provide some mass or some energy, this is no longer equal to 0. This is tangible. And this is essentially measuring, this is proportional to how much the universe will curve, how much space-time will curve around this specific body. So that means that if I increase this, this curvature increases, and so on and so forth. So this is essentially how gravity works. But here's the thing. There's something called the principle of least axes.